parameters and variables, putting those in. And then you actually have to, if you set it up, you might have to move the reference frame, because you want to make sure that in Compsol that this, we'll go to the geometry. So you make this, you put circles in here, and you see how I set up everything with 0, 0 as the first circle here?
Mm-hmm.
So, but then I did is, my 0, 0 is here, because I moved the entire assembly. So I moved my whole assembly, so my beta, which is the center of mass, is here. So I moved it that distance, which you determine using SolidWorks to find the center of mass.
Okay, so just go slowly. So number one, you use this move command in the geometry to move the entire module a certain displacement that you can go X and Y here.
Yeah, exactly.
And then the reason we do that is that we want to move to the center of mass of the system. And why is that?
Because these equations, some of them have X in it, like specifically body loads. If you look at the body load equations, there's an X and a Y, and so the body load changes depending on where you are in the connecting rod, your X and Y position. And so to reflect that, the equations were based on an XY coordinate system at the center of mass.
Center of mass, okay,
Yeah.
that's, I have to clarify that.
So that's why you have to change it. So if we go back to here, that was just talking about moving it using that parameter. And then loads and constraints, so so you want to make sure that the 2D model has, so in Compsol, so to make the geometry, you can just right click. You can always, in Compsol, right click and add things to that. So this is the geometry, so I added all the geometry. In the model, I can add the variables, I can add the parameters. In the solid mechanics, this is where you add how you're analyzing it, so that it should have some linear elastic model. So in that I say that, I want to analyze it as isotropic. I want to analyze it with the Poisson's ratio, and I want to give it, so you can set this up as E, nu, and rho, based on the fact that your parameters has E, nu, and rho. So you plug in these numbers, and then you don't have to keep manually changing it. So that's, and then you can force linear strains. You can. This is how your model's set up. In the solid mechanics part, if you just click on this, you can see that this is plane stress. I want it to be plane stress because it's thin. I can give this whole model a thickness.
Okay, but before you do that, you have to tell them that they have to select the regions in the model. Like up there, you have 1, 2, 3. This is the first step, that they have to select what they want to apply the solid mechanics module to. So you have like 3 regions.
Yeah, if you say all domains, it will take everything. And then later on, I'll show you, like, I guess I can just say it now. Later on, you're going to do something where you can change thickness. And because I have these as separate domains now, I can select these to be that, and I can change the thickness. So now you can actually add, 3 dimensions related to the analysis. And then I can change that thickness. So in here, anytime you do this, so I can say I can delete that, and then I can select this. I don't know why that was. I should be able to select this. I don't know.
Yeah, it's okay.
I guess it always works better with all domains. But other properties, like for example, prescribed displacement, I can remove this like that, and then I can select. I don't know what's going on. You usually can select.
I think maybe it's disabled. Select.
Add a selection. Unless the screen isn't updating or something.
Yeah.
I don't know. Sorry.
Okay.
Yeah, I don't know what's happening. It could be the remote. Because let's try it on this. Fixed constraint. I'm gonna just delete this. Delete. Okay. Then I'm gonna. So I'll show you. You can add a fixed constraint to the body, like fixed constraint,
Mm-hmm.
and then I'm gonna select in this. Select this domain. Create selection.
Hmm.
It's like it's not even letting me click.
Can you
it.
do all domains and then just start deleting the ones you don't want?
Yeah. That's
then
really
subtract.
weird though.
Hmm.
That,
That's
I, don't,
select.
I don't know if it's because it's the version of Comsol I downloaded or something.
It's an online version right now. You're working online.
No, I'm using this other, what the other guys gave me. So it could just be that.
Yeah, it could be.
It's weird. But yeah, you can, delete away stuff. But yeah, you can see how
I mean,
normally you would be able to select this. I don't
Yeah.
know why it's not working.
It's good that they see the kind of difficulties that
Yeah.
you would have.
Yeah,
Technical
it's really
things.
odd. I know when we ran it at the school version. The school version will let you. I think this is just a glitch in the version.
In the version, yeah.
Whatever
because-
version I have, it's just
Yeah.
it's rather odd. But yeah. Okay, so we can. So anyways, let's get back to what the. So what you need to do to set all the constraints is you wanna, like I was saying before, you want to fix this pin right here. So if you go to fix constraint, that one's fixed.
Mm-hmm.
And then, so you want to fix this one, and then what we're going to do is we're going to have this pin, it can be free to move this way, but it can't move up and down. So
Mhm.
this pin can run into the connecting rod, and the connecting rod can run into the crankshaft pin, and so you can get contact from that. So
Basically, you have contact on both ends, right? You have the contact pairs.
yes. Yeah, so to create that, so in this module, you have to make sure that you create contact pairs.
Mm-hmm.
So you can see contact pairs up here. I have a contact pair and I have a contact pair.
Mm-hmm.
So it knows it's two separate, this is an assembly, that these are separate parts, and that these are in contact. So I fixed this one, and then I made a prescribed displacement on this one. So again, all you have to do is go right click, and these are
And
bodies.
Daniel, the material properties for the pins are different from the material properties for the connecting rod.
So that comes from this. These are the only material properties I put in, is E, nu, and rho, and they are the same material.
They're the same, yeah. But in principle, you can change the material properties for
'cause I can go like
can make them
this.
harder.
I can add another linear
Mhm.
elastic model.
Yeah.
And I can select different. Yeah. See, I don't know what's.
Yeah.
going on.
Yeah.
I don't know if it's the screen because I'm connected or it's rather weird. Yeah, this is still working. Okay, but yeah, so.
Yeah.
Maybe if I go like that and then
Yeah,
Okay.
there's a screen. So because it's, I think it's not responding because it's online. Like,
Okay, well anyways, yeah. So, and you can just delete any of these. It's all just right-clicking. Delete to right-click. So you want to put a prescribed displacement. So again, you can just go right-click. And these are all bodies. So like you can do a fixed constraint, but this is for a line. So like on a boundary. But this is like I want the whole body to be fixed. So that I can go to more and prescribe a displacement. So I already have that one. And so I just selected this pin
Mhm.
and it say that, oh, in the V direction, which is up and down, it's 0. But it can still move in the U direction, in the axial direction. So then for the contacts, you want to make sure that you select 1 and 2. Like the screen will come up and you just select this and then go shift and select the next pair. But once you touch it, you don't want to touch it again essentially because like I don't want to touch this and unclick it because there's apparently a glitch in COMSOL for some reason that.
I remember you guys suffered with that one.
Yeah, because we couldn't figure out why it was doing it, because it was doing, like, you can have two completely exactly identical files except for you undo the contact for 1 second and then you put it back on, and it will error for some reason. So I think it's a glitch in how they set up the program or something. So yeah, so once you set it up, you don't want to probably touch this again. And then this is the penalty factor. We also noticed that the penalty factor wouldn't converge right, and we went online. There were some issues, but they were saying that if you use the Young's modulus and you just divide by the I think it's just, the h is the size of the mesh, so we'll take the lowest, smallest size mesh, because like in your mesh, all these have different sizes, but it'll take the smallest size and use that, and that apparently was a good enough parameter that it works pretty well.
So H is, how does it know H?
H is built into the program. It will pick it up. You don't have to prescribe it. Just like X and Y are already built into the program. Like you don't say X is 1 or X. You know what I'm saying?
So H is the mesh size.
Yes, it's the mesh size. It's already known in the program that if you use a parameter H, it's going to use that.
Okay.
So yeah, so that's pretty. So once you set this up, don't unclick this, or that's probably bad. So then you want to put in your loads. So you have the body loads for the connecting rod, right? So to do that, you just plug in. You want to make sure that the load is per unit volume, so it's a real body load, and then you just type in BA and then BT, and then if you go back to here into variables, you can see that there's an equation for BA and BT, and they're all based on X and Y, as in it uses the X and Y coordinate of this, which it already knows. So that should be pretty much, and then you want to put an axial load on this, right? Because this is fixed, but this still has axial load caused by the piston, pushing down on it. So this is just the force PRA, which is you did this in the load analysis and everything. Again, it calculates it. And this is a total force, though. It's not force per area. It's a total force. So if you just set it up like this with these constraints, you should be good. So everything else is defined, material, definition. Then you just go to this mesh, and then you can do physics-controlled mesh. Or you could try to do user control and put in element. The physics-controlled one does a pretty good job, as you can see. I mean, for a basic analysis, and you can do extra fine, you can do normal, but normal you can see it's extremely coarse, so you're not, but still it's physics-based, so then it understands that you're going to have a lot of stress concentrations here, so it puts a little bit more there, I think. So, but you probably want to do, you can start off with normal to make sure it runs,
yeah.
And then go to fine, and then, probably finer, and then, probably extra fine is definitely good. So it just takes a little bit longer each time, obviously. And then this is the study you're running. So if you just put in a phi, if you want to just check to see if this is running, you can go to parameter. I can put in a phi, and this is in radians, not degrees. So you can put in pi or whatever for that, and you can check it. Now, when you want to actually do the parametric sweep and go through all the angles, then you want to set this up as a parametric sweep. So first I just do is I can add a parameter. So I added phi. I'd already done that, phi. And then I can put a range of, okay, so I start with -2 pi time, and then I go to 2 pi. So, whole 360 all the way back. And then I can do steps of, you can set it up for pi over 10 or something like that, but for every angle you probably want pi over 180, so.
Right.
So to do this range, you right-click on the parameter?
Oh, you just click this range
click on
button.
the range, okay.
Yeah.
Nice.
And then you can, add. And that's then it's pretty much set up. Now there's some features that you can, like, keep solutions in memory only the last time, because then the solution builds up and then your file gets really big if it's holding all your existing solutions. So I think that's pretty much it. Save each solution in a so, and this is just the step. You don't have to make any modifications to this. This is the solver. You don't need to. So all you need to do now is go right click and then compute, and it will run the analysis. And here, let's just try compute. Or,
But you made
did I
some
have
changes,
anything?
yeah.
Did I? Oh, I have this. Yeah, I think it should run. Okay, so watch. You can see at the bottom of the screen right here, it will show you what so now it went through the preliminary analysis, the preliminary thing, and now it's starting the analysis. As you see, it's going to take. You can see this bar increase, the green bar, and when the green bar gets all the way up to here, it will be done. So, it's probably taking a while because the finer.
Because
mesh.
you're doing it for extra fine, yeah.
Yeah, so I can cancel this, and then cancel the computation. So let me go back. Let's just set this
You can
to
do it for a coarse mesh.
normal.
Normal.
Yeah. Let's just try see how. I think it's pretty fast on normal compute, and then you can see that. It's still. Oh, I also have 180. I mean.
Per each degree, right?
Yeah.
Have 180, oh yeah, this
Yeah.
is a lot of
Higher than
fives,
10.
yeah.
But it will definitely
Yeah.
get up there, and it will
Yeah.
essentially when it's done, it's done. So then
Yeah.
you'll go to the results section, and it will automatically give you, because it's a structural module, it will automatically give you a stress plot. So this is, so you can select this, but really to modify it, you want to go to this surface, and then this is the deformation. So what this does is that I can change the deformation scale. So it's hard to see. Okay. So, for example, if I go to this surface plot, and this is, I don't think it did it right,
You interrupted.
because it's saying I have essentially these,
Yeah,
You
because I
interrupted
think
the
I interrupted the
calculation.
calculation.
oh yeah, we didn't run it,
Yeah, then
but it should, because it deleted the old one.
Yeah,
Yeah.
once
Here,
you
let me
start.
just, let me just go and set this to,
pi over 10.
yeah. And then run this. See, it's going pretty fast now,
Mhm.
so it shouldn't take that long. If we can look at the other one.
So Daniel,
This-
for the parametric sweep, can you have one of the geometric variables as a parameter? For example, if you want to look at the effect of the fillet on the stresses, can you make the fillet radius to be a parameter, and then it runs like
You
this
could,
way, or
because
is it difficult?
We did in the geometry.
Yeah.
We went and in this one it's not. Let me go back to this other one. While it's running, I'm pretty sure you can. Oh, apparently you can't move it around. Yeah,
to
while it's
win the-
running you can't. But in this one I didn't put a fillet on there. But you can, like, if you wanted circle size,
Circle
right?
size,
I can
yeah.
put this as a variable
Mhm.
in my parameters. You know, put that as a variable, and then put that variable in here,
Mhm.
and then in the parametric sweep, I could sweep through saying,
Mhm.
what if I want to change the radius
Right.
of
Mhm.
this?
So
you know?
can some of the students make optimization for the shape, for example? If you just, instead of running it, you can have like a few geometric parameters, and then you can sweep through those, and maybe you have an objective function if they want.
You could change the thickness of this,
Yes.
and then just kind of go through and do some basic preliminary,
Mhm.
sweep. Because, I mean, but obviously it's not going to do. It's only changing one parameter at a time.
At a time, yeah.
So, but yeah, you can do multiple, I guess, iterations then, because it would fix the phi, and then it would sweep through thickness, and then
Mhm.
maybe you could sweep through length, and then you could sweep through.
Right.
So yeah, that would be a lot of data,
Mhm.
but
Actually, in advanced design, then you have like another I think there is a feature in console where you can set a objective function, and then it will just kind of keep going through it until it optimizes it.
So
But that would
this-
be, when we modify the course, this will be another a nice feature for the design
That would be
to introduce
very
optimization.
yeah. So yeah, it just ran. So I have a couple. So you can see that it bent. It was deformed a little. So in the scale, the deformation scale, you can go to here, and I can make this 1,000 or something, right? And then you can repaint. This is always to replot it, and you can see you're just changing how much it's going to show up.
Mhm.
And if I set it to 1, you can see like clearly, that's realistically, it's very small deflections. So so if we go through, you can go through like all the connecting rod angles. So at 0, you expect it to be in compression, right? Because the piston's at the highest. It's if you go back to the you know, this is your the plot up here, 0. You're getting a lot of, you know, axial loads from the pressure of the piston. So.
Okay, now I have another question. We have all of the deformations, say, as a function of phi. Can I highlight all of the files and then make a movie of the motion?
This is exactly
I think it's
what
possible.
we have down here.
Mm-hmm.
You can go export,
Mm-hmm.
and you can go animation, and then in this animation you can just go and you can run it.
So you highlighted the parameter values that you want.
Well, yeah, you can save this as a movie,
Mm-hmm.
or you can just go in the stress plot. You can go and you can say, if you hit this play button up here,
Mm-hmm.
you'll go play, and then it will start going through. There you go. See, that's the whole range of motion.
Yeah. Okay.
So.
All right. Good.
So yeah, you can do that, or you in here you can actually in the animation thing you can save it as a file, I think,
Yeah.
the advance or something like that. But yeah, there's all. I mean, you can go through. Yeah, you can save it as a GIF movie file or something. And then so the other thing you want to do is at some point you need to export the data so you can run the fatigue analysis on it. So if you go to data, you can go and you can put data in there, and then here's the data file, and you can select all of the crank angles, right? You want to select all the fees, and then this is where you're putting in the expression that you want. So you can go down to here and you can set the file. So like let's say I just want to put it, you know, somewhere on my desktop, just this file, and like, you know.
Yeah, this step is very important because this is post-processing.
Mm-hmm.
So you can get the data, any displacement or stress or strain, and then you can take it, export it, and then you at every nodal point, right?
Mm-hmm.
And then you could do specific analysis with it.
So I'm just gonna make some file and then, you know, spreadsheet type, and then what I want to do is I can hit this add expression, or I can replace the expression. There's already an expression, and so this is important. So you can export any data you want. Like here, H is the mesh size.
Yes.
You can do the coordinates. You can do in the solid mechanics. You can do, you know, your loads, and this is you can do the stress, and you can plot the. You can get the stress invariance, you can get the stress tensor, and that's what we're going to do. We're going to get the x component, and the xy component, and the y component. But you can just grab the von Mises stresses if you want, and if you can, or you can do whatever you want, even material properties. If it's
for example, when we were trying to apply the ITER criteria, we wanted to have like section stresses, then we can get the entire field, and then we can average sections and get membrane and bending stresses and apply the criteria.
Exactly. So you can just select, I'm going to just select this X component, and you can see that that's the tag. So that name that's associated with it, where is it exactly? Stress tensor. See solid.sx. Solid.sxy. So you can just go in here if you want and just modify this, and like I'm just going to get the y now. So and then so you get the expression down here, and then you can change the description. You can say, you know, if you want, that's y. But the other important thing is that in this advanced feature, you probably want to not include the heading, so you want to remove that. Because if you include the header, sometimes when MATLAB, you import the file, it gets confused. I had some people that way, they're like, oh, it's not reading the file right.
Yeah.
So if you just get rid of the header, because when we already know how the file is going to output, and so the MATLAB program's based on that already. So it should output correctly. So yeah, so I'm just going to do that full precision, and then I can export this.
So when it goes out into MATLAB, then you have the structure of the file is going to be like a node number and the connectivity and coordinates, and then the value.
I export the file,
Yes.
and then we can look at it. I just export it to my desktop.
Then I can do any analysis with MATLAB or any other code.
And then I just put it down here. So this is what it comes out, but like I didn't have a header on there. But I'll show you what a file with a header, what it looks like, because it's I have some files already set up for the fatigue. So if I go to this one, oh, actually, so yeah, this is better, but really what it's doing is, this is the first one is, I think it does fees. So it starts with fee 1, fee 2, fee 3, and it goes through all the fees this way. It goes through all the fees, and then it goes through this, is the first two columns are the location, the coordinates, so the x and y, and then these are just all the stress values. So you can see how this is not a stress value, that's not 10 to the 7th, but this is 10 to the 7th. So the first two columns are just the coordinates, where the node is located. The next one is the stress number for phi 1, then phi 2, then phi 3, and then, you know, and that just keeps going. So that's how the file is put. So
it's not really an organized file. Like if you want to do some post-processing, you have to really know when the line starts, the next
when
line
you put in the
starts.
header, it shows you.
Then it shows you.
That's
yeah.
how we figured it out. But we
Yeah.
removed a header because sometimes when you export to MATLAB,
Yeah.
it's so. But now that we know how it's written, like we already wrote these M files to run like that.
Yeah.
So if you want, we can run through. So that's essentially all of this analysis here. I pretty much touched on everything: meshing, the solver,
Yeah.
and the only other thing is that then you want to change the thickness, right? So then you just go to in Compsol. You go to this one. See, I already done it for here, but I would just right click and say change thickness, and then I can select domains. Well, for some reason this program's not, but when you do that, you can select all these domains and change the thickness. So.
Okay.
So that's pretty much all of that, the player, and so these are some examples of what you should get, right? That's the contact stress, and then so, and this is what happens when you vary the thickness here. This is kind of important. So varying thickness is very good because like as you can see, that's a contact stress, and this is all the same thickness. But if I increase the thickness of just this ring here, then this point is virtually not in contact with anything. This is just the contact stress. So I reduce the contact stress, but I've only increased the material just a little bit amount, just around where the ring is. Because the beam, I didn't have to increase the whole thickness of the beam. This is essentially the same analysis, you know. So it definitely helps optimization. Just
That's
by
a good
beaming.
point about optimization. So you're doing it actually manually by just going and changing the thicknesses.
Yeah, but like you said, you could do a parametric sweep where the thickness of this whole thing is just a variable.
The variable, and then you can look at the content.
Yeah.
Okay, so now is the post-processing for fatigue analysis.
Exactly. And this uses the Paul-Grin Minor linear damage model, which is just essentially 1 over the damage gets you, the life cycles. So, and then you just add up how much damage in the life cycle based on the SN curve. So what we're doing is, so normally you have multi-axial, it's time dependent, and it's all through the body. And what we're doing is just doing an approximation based on, okay, I'm going to take a node here. So every element, has a node. I'm going to take its spatial coordinate, and then I'm going to calculate the principal stresses based on the sigma x and y and tau xy. So you export in Compsol these files, sigma x, sigma y, tau xy, and then import them in, and then we calculate the principal stresses. So it becomes a biaxial problem now. And so you're essentially doing an SN curve where it's axial loading in one direction and then axial loading in the other direction. And then we do rain flow counting cycle method on it, which is essentially shown here. So you go through this, and so I wrote this program. To check this, you can use this as like homework or anything, because this file will essentially go through, and I give it like 1, 10, 5, like a counting cycle with the peaks like this, and then it will give me the max stress of the half cycles, the minimum stress of the half cycles, and then I can calculate the mean and alternating. So that this whole program, just this one rain flow counter, will do this whole counting of the cycles. So that's just one part of it.
So it's a function, MATLAB function? That you
Yeah, I
wrote?
just wrote this MATLAB function.